Welcome to this explainer. If you write code, you already know the universal sinking feeling. You hit run and nothing. Or worse, it quietly spits out the completely wrong answer. It's incredibly frustrating, right? But today, we're going to flip the script. Instead of viewing broken code as a personal failure, we're going to treat it as the start of an exciting, evidence-based investigation. You're no longer just a programmer. You're a detective. And your code? It's left behind a trail of clues. Let's get into it. So let's start with a foundational question. Why do programs fail in the first place? Sure, it could be invalid data or wrong conditions, but at a much deeper level, they fail because there's a huge gap between what you assumed your program was doing and what it's actually doing. The machine literally doesn't care about your intentions. It just blindly follows instructions. Debugging is all about shining a light on that gap to uncover the hard truth of your program's behavior. Okay, here's our playbook for today. 1. The art of debugging. 2. Meet the 3 bugs. 3. The 4 debugging tools. 4. Fixing a logic error. And finally, 5. Avoiding common mistakes. Part 1. The art of debugging. Your investigative protocol. Look, debugging isn't some chaotic guessing game where you randomly change lines of code and just pray that it works. No way. It is a deliberate, methodical process. And here is the strict 5-step protocol you should follow every single time. 1. Reproduce the error. 2. Observe values and control flow. 3. Identify the cause. 4. Fix the cause. And 5. Test again. Notice anything interesting here? Fixing the cause is step 4, not step 1. You absolutely have to gather hard evidence in step 2 before you ever dream of jumping to a fix. Debugging is not random guessing. You gather the facts first. Moving to section 2. Meet the 3 bugs, identifying the suspects. To catch a culprit in your code, you first have to know exactly what their MO looks like. Suspect number 1 is the syntax error. Honestly, this is usually the easiest one to spot because the program won't even run. A syntax error basically means your code broke the strict grammar rules of the language. Think of a missing colon at the end of an if statement, or maybe an unclosed parentheses. The computer is incredibly pedantic. If the grammar isn't perfect, it simply refuses to play ball and stops right in its tracks. Suspect number 2 is the runtime error. In this case, your syntax is totally fine, and the program starts running. But suddenly, bam! Right in the middle of execution, it crashes. This happens because the program is asked to do an impossible operation, like trying to divide a number by 0, or trying to open a file that literally doesn't exist. It hits a sudden, fatal roadblock. And finally, the stealthiest suspect of the bunch, the logic error. What's really interesting here is that there is no crash. The program runs perfectly smoothly from start to finish, but the final result is completely wrong. These are incredibly tricky because the computer thinks everything is absolutely fine. Catching these little stealth bugs requires real, careful observation to find exactly where the logic went off the rails. So how do we catch them? Section 3, the 4 debugging tools, building your forensic toolkit. We've got 4 distinct techniques to cover, and each one gives you a very different kind of evidence to help crack the case. Technique number 1 is the trace table. Think of this as your meticulous forensic ledger. A trace table records exactly how variable values change as a program runs over time. You map it all out step by step. This technique is an absolute game changer for tracking down logic errors, especially when you're dealing with complex loops where values update super fast. Let's trace the evidence. We start with a total of 0. In loop 1, the input is 4, so the total becomes 4. In loop 2, the input is 3, jumping the total to 7. And in loop 3, an input of 5 brings our final output to 12. You see how this brilliantly illustrates those hidden changes? It gives you absolute, written evidence of exactly how the final answer was calculated. Technique number 2 is the good old print statement. If trace tables are a meticulous ledger, temporary print statements are like shooting flare guns right up into the sky. You drop them into your code to display variable values in real time, or just to confirm that a specific part of the code was even reached. They're fantastic for a quick check. But, a quick word of warning, too many print statements can quickly make your output a massively cluttered mess. So label them and definitely remember to delete them when you're done. Technique number 3 brings us to breakpoint debugging. This is a massive upgrade for your toolkit. A breakpoint is quite literally a marker you place on a specific line of code. When the program reaches that line, it freezes time. It pauses execution completely, allowing you to step in and inspect the exact current state of all your variables. Once time is frozen, you get to use our fourth technique, step-by-step code execution. This lets you watch the control flow line by line. You've got three main moves. You can step into to dive deep inside a function call. You can step over to run the current line but skip entering any underlying functions. Or you can step out to quickly finish the current function and jump right back to where it was called. It's like watching your code run in slow motion. Let's weigh two of these tools against each other. Print statements, great for fast checks, super easy to add, but the output gets super cluttered. Breakpoints, on the other hand, let you pause cleanly at key lines to inspect the exact state without messing up your final output, though you do need an IDE to use them. The big takeaway? A strong programmer doesn't blindly rely on just one tool. They mix and match based on the actual problem they're facing. All right, Section 4, Fixing a Logic Error, Investigating a Crime Scene. Let's put these tools to work on an active case. We've got a program meant to count even numbers from a list. It runs perfectly, no crashes, but the final count is wrong. We have a classic logic error on our hands. If we set a breakpoint inside the loop, or maybe use a trace table to track our variables, the hidden truth comes out. Look closely at the condition we're using. It says, if n modulo 2 equals 1. By tracking our loop cycle, we'd immediately see this code is actually counting the odd numbers. The logic error was hiding right there in plain sight. Changing that 1 to a 0 fixes the entire program. This is the real magic of observing control flow instead of just staring at the screen and hoping the answer jumps out at you. Section 5, Avoiding Common Mistakes, Rookie Detective Traps. We've caught our bug, but before we wrap up, we need to talk about amateur habits that will totally sabotage a good investigation. Here are the rookie traps you absolutely must avoid. Number 1, changing code and guessing a fix too early. Seriously, before you change that code, what's your evidence? Number 2, confusing logic and syntax errors. Don't assume that just because a program runs, the code is totally correct. Number 3, burying yourself in too much info by spamming print statements. And finally, skipping the retest. Listen, a fix isn't real until you have retested the program to confidently confirm that the original bug is entirely gone. If there is one big idea you take away from this explainer, let it be this. Debugging is most effective when it is deliberate, evidence-based, and systematic. A methodical investigation is always going to beat frustrated guessing. Stop blindly changing things, start observing, and treat your code like a puzzle just waiting to be solved. I want to leave you with a quick challenge for the next time your code throws an unexpected result. Ask yourself right now, which debugging technique will you use first for your next logic error, and why? Will you draw out a trace table, fire a print statement flare, or freeze time with a breakpoint? The choice is yours, detective. Keep building your toolkit, stay curious, and happy debugging.